Have you ever gazed up at the night sky and wondered about those faint, fuzzy patches of light? They aren't just single stars. They are entire galaxies, vast cosmic islands, each containing billions or even trillions of stars. But not all galaxies look the same. They come in a stunning variety of shapes and sizes, each telling a different story about its history and evolution. The two most common types you'll find are spiral galaxies and elliptical galaxies. Let's embark on a cosmic journey to understand what makes these two galactic shapes so fundamentally different. We'll explore their structures, their star populations, and the dramatic processes that sculpt them over billions of years. Spiral galaxies are perhaps the most iconic and photogenic of all galaxy types. When you picture a galaxy, you're probably thinking of a spiral. Our own Milky Way is a prime example, a majestic, sprawling city of stars. The defining feature of a spiral galaxy is its distinct structure. It consists of a bright central bulge, a flat, rotating disk of stars and gas, and of course, the beautiful spiral arms that give it its name. These arms are not solid structures like the spokes of a wheel. Instead, they are density waves, areas where gas and dust are more compressed. Think of it like a traffic jam on a cosmic highway. Cars, or in this case, stars and gas clouds, move through the jam, slowing down as they enter and speeding up as they leave. This compression within the spiral arms is incredibly important. It triggers intense bursts of star formation. The immense pressure squeezes clouds of gas and dust together, causing them to collapse under their own gravity and ignite into brilliant new stars. This is why spiral arms are so bright and prominent. They are filled with young, massive, hot blue stars that shine with incredible luminosity. These stellar nurseries make the arms stand out against the fainter backdrop of the galactic disk. The central bulge of a spiral galaxy is a different story. It's a tightly packed, roughly spherical region of older, cooler stars. These stars tend to be redder in color, and they follow more random, elliptical orbits around the galactic center. Unlike the orderly, circular paths of stars in the disk, the size and brightness of the bulge can vary significantly from one spiral galaxy to another. Some, like the Andromeda Galaxy, have large, prominent bulges, while others have much smaller, almost non-existent ones. At the very heart of most large spiral galaxies, including our own, lurks a supermassive black hole, a gravitational titan millions, or even billions of times the mass of our Sun. The entire system bulge, disk, and arms is embedded within a vast, invisible halo of dark matter. This mysterious substance doesn't emit or reflect light, but its gravitational influence is what holds the galaxy together and keeps its stars from flying off into intergalactic space as it rotates. Spiral galaxies are dynamic, active places. They are rich in the cold gas and dust that serve as the raw fuel for creating new generations of stars. This continuous cycle of birth and death makes them vibrant and ever-changing. Now, let's shift our focus to the other major player in the galactic zoo, the elliptical galaxy. If spiral galaxies are bustling, star-forming cities, then elliptical galaxies are like ancient, quiet metropolises. Elliptical galaxies are vastly different in appearance. They lack the flat disk and graceful spiral arms of their counterparts. Instead, they are smooth, featureless, three-dimensional blobs of stars, shaped like an ellipse ranging from nearly spherical to highly elongated, like a cosmic football. Their appearance gives us a clue about their internal dynamics. Unlike the organized rotation of a spiral galaxy's disk, the stars within an elliptical galaxy move on random, looping, and crisscrossing orbits. Their motion is more like a swarm of bees buzzing around a hive than cars on a circular racetrack. This chaotic motion is a relic of their violent formation. The leading theory is that elliptical galaxies are the end product of major galactic mergers. When two or more large spiral galaxies collide, the event is a cataclysm of cosmic proportions. During a merger, The immense gravitational forces tear the delicate spiral structures apart. The orderly disks are disrupted, and the stars are thrown into chaotic orbits, mixing them all up into a single massive spheroidal entity. It's a process of galactic scrambling that unfolds over hundreds of millions of years. These mergers have another profound effect. They trigger a final spectacular burst of star formation. The collision violently compresses all the available gas and dust, igniting a galaxy-wide firestorm of new stars. However, this starburst is a final glorious hurrah. The intense radiation and powerful stellar winds from the massive number of new stars, combined with activity from the central supermassive black hole, effectively blow away or use up all the remaining gas. Without this raw fuel, star formation grinds to a halt. The galaxy can no longer create new stars. This is why elliptical galaxies are often described as red and dead. The stars that populate them are predominantly old and cool. The hot, bright, blue stars that illuminate spiral arms have long since burned out and died. All that remains are the long-lived, less massive, redder stars, giving the entire galaxy a characteristic yellowish-red glow. The number of stars they contain is also a key difference. While a spiral like our Milky Way has a few 100 billion stars, giant elliptical galaxies can be true behemoths, containing trillions of stars. They are the most massive galaxies in the universe, often found at the heart of large galaxy clusters, where they have grown over cosmic time by consuming smaller galaxies. So to summarize the key differences, spirals have a disk and arms. Ellipticals are smooth spheroids. Spirals have organized rotation, while stars and ellipticals have random orbits. Spirals are rich in gas and dust and are actively forming new stars, giving them a bluish tint. Ellipticals have very little gas and dust, have ceased star formation, and are dominated by old red stars. Scientific research, particularly from telescopes like the Hubble Space Telescope, has provided incredible evidence for this evolutionary pathway. We can see galaxies in various stages of collision and merging, capturing snapshots of the very process that turns two beautiful spirals into one giant elliptical. Computer simulations also support this model. By inputting the laws of physics and gravity, astronomers can model the collision of two virtual spiral galaxies and watch as they merge and settle into a structure that looks exactly like a real elliptical galaxy. The number of such simulations showing this outcome is a powerful confirmation of the theory. So, when you see a spiral galaxy, you are looking at a relatively undisturbed, evolving system, peacefully churning out new stars. When you see an elliptical galaxy, you are likely looking at the ancient remnant of a dramatic and violent past, a testament to the powerful force of galactic cannibalism. Both shapes, in their own way, are beautiful and fascinating. They represent different paths in the grand story of cosmic evolution, showing us that the universe is a place of both serene creation and violent transformation. Thank you for joining us on this tour of galactic shapes. To learn more about the wonders of the cosmos, be sure to subscribe to Space Repo.